So just a reminder, 3 class periods from today, we have our first exam, the 17th. So you know, make sure that you're getting all of your homeworks and your quiz done by then.
Do you get the whole class for that?
Huh?
The whole class for that? You get the whole class for you?
Yeah, you have the entire class period for the exam. So I believe we left off with this example. I'm not quite sure how far everyone got into that, but I know we had, significant, I guess 10 minutes worth of time is not significant, but we had some time to work that. Was anybody able to come up with 3/2? Okay. So as a reminder here in 6.5, what we're looking at is arc length. And the arc length formula involves taking the square root of 1 plus the derivative squared. So we have to find the function's derivative, then we square it, then we have to add it to 1. And nothing here gets terribly fancy because our integration techniques are really limited at this point. So anything you encounter up until chapter 8 will be, a familiar antiderivative, hopefully, or a u substitution. So our derivative, y prime, is 1/2 times e to the x minus e to the negative x. And we'll actually see both of these functions at the end of this unit. So in 7.3, when we talk about hyperbolic trig functions, these two functions, our y and our y prime, show up in a different context, but they're the same functions do show up. All right, so there's our derivative. Then we have to take our derivative and square it. So remember to square both terms. Now, just like a lot of calculus problems, or even problems in Calc 2, you do a little bit of work to set it up in context of Calc 1 or Calc 2, but then like the vast majority of what you do is really algebraic, right? So that's a lot of what we do. So don't take that stuff for granted. I know like you feel rushed on an exam, so you're like, oh yeah, derivatives, I got this. Squaring stuff, easy, right? And so typically that's where the most common mistakes are made with those, not with the setups, but with sort of those intermediate steps. So we'll see if we can get this to come out correctly. Let's just go ahead and square this instead of leaving it in sort of factored form. I'm not sure what approach you all took. But so we'll have this 1/4, we'll square the e to the x stuff. So we have e to the 2x. We have negative e to the negative x times negative e to the negative x. The positive e to the 2x. And then we have twice their product. So their product, we have e to the negative x times e to the x. So that gives us e to the 0, which is 1. And it's negative. And then we have twice that product, so we have negative 2. And then since our next step is to add 1, let's go ahead and distribute the 1/4, just so we're, not trying to add 1 inside the parentheses. So there's y prime squared. Then I'll just write this. We're going to add 1. So when we add 1 to this, we have e to the 2x over 4 plus 1/2 plus e to the 2x over 4. Sorry, that's negative 2x, my bad. That's from this second term squared. So negative 2x, negative 2x. Excuse me. So see, there you go, that's all you needed, right? I forgot that negative, the rest of the problem's wrong. I do give partial credit, because those mistakes do happen, and it's not totally detrimental to the outcome. Okay. So that's our expression that we're going to throw underneath the square root for the arc length formula. But again, since we're taking the square root of that, we want to see, is that an actual perfect square? So we don't have to deal with taking the square root of something. So how would this expression e to the 2x over 4 plus a half plus e to the negative 2x over 4, how would that factor, or is it a perfect square? Yeah, how do we know it's a perfect square? Do what? Yeah. So it's just, we know that when we squared this quantity, we ended up with this expression with a negative 1/2. When we add 1, we just get a positive 1/2. So the only difference between the sum of squares or the difference of squares is that middle term. So one of them's positive, the other one's negative. So how would this be expressed as a square? Mm-hmm. So e to the x over 2 plus e to the negative x over 2. And again, what the... No, because it's squared. We're going to take we're basically take the square root of this to get over here inside the square. So I just want to make sure that this is 1 plus f prime of x squared. All right, so then in order to find the arc length, we take the integral of the square root of 1 plus f prime squared. We just take the square root of all that stuff, which I'll just go ahead and put here. With respect to x, and our bounds were from negative ln2 to ln2. All right. Does that make sense? Does anybody have any questions on that? Let's go over here. Negative ln2 to ln2. And then we're just integrating e to the x over 2 plus e to the negative x over 2 dx. So personally, I would take the common factor of 1/2 out, and then take the antiderivative of e to the x and e to the negative x. Okay, so there's our antiderivative. Leave this out here. Evaluated at a, we have e to the ln2 minus e to the negative ln2. So f of b minus f of a. Oh, sorry, there's a negative there. E to the negative ln2 minus e to the ln2. So just a reminder, when you evaluate e to the negative ln2, write this out. E to the negative ln2, you want to put that power -1 up there with the 2. So it's just e to the ln of 2 to the -1, which is e to the ln of 1 over 2 to the first. So that's just e to the negative ln2 is 1/2. There's a few in your homework where you're evaluating E to natural log powers. So if you've done some of the homework, you've seen that a few times already. Okay, so that's pretty much it. Let's compute that. We get our 3/2. So we didn't have a graph there, but. So we can sort of visualize what we're measuring there. So we've measured the length of that curve right there. I guess it doesn't seem too glamorous, but. We'll just put that here. Anybody have any questions about that? So that's arc length. How do you measure the length of a curve? Again, we see that defined in terms of integrals. And chapter 6 was about applications of integration. What can integration do for us? So we've seen velocity displacement. We've seen areas between regions. We've seen volumes. We've seen here in 6.5 measuring lengths of curves, and continuing with the next section, integrals also allow us to measure surface area, the area of a surface bound by a function revolved around an axis. So not only can we measure the volume of that, we can measure the surface area. And so the idea is still is the same. We cut into this three-dimensional object. You know, what do our cross sections make? Here's a cross section. Here's that same cross section here. Just make it a little larger. The same cross section magnified here. And so what we're looking at is that's still the general slicing method. What is the area of our cross sections? So we can come up with a formula for this. Well, all of our cross sections are frustrums. They call these things frustrums of a cone. And then this is kind of your book's derivation of the surface area formula. So if you're interested, you can definitely reference the textbook. The way I like to think about it, how the surface area formula comes about, is let's just think about a right circular cylinder for the moment. I think we have that. Try to draw this. So if we had to measure or calculate the surface area of this thing, we'll call surface area what do they call it? Capital S. So how would we compute the surface area of this circular cylinder here? Think about what gives you an area. Yeah, the circumference times the height, right? An area is just a linear dimension times a linear dimension. So we take and in fact, all of the cross sections are circles. I should do that in a different color. We take the length of all of our cross sections, whether it's that circle or whether it's that circle, etc. Take that length, which is the circumference of the circle, and then we multiply it by the height. Okay, so surface area just, in that sense, is the circumference times the height. Or of course we know the circumference is what? Defined how? 2 pi r. Pi r times the height. All right. So now something more elaborate like this, whatever this solid up here. Let's say that's f of x, and we're going to revolve this around the x-axis. And measure the surface area of that figure. The idea of how we applied, if you need to think about it, just rotate that cylinder 90 degrees. We said when we cut into this thing, all of those cross sections are still circles, so we still have that length, 2 pi r, for the length of the circle. But of course we know, we can see that throughout, let's label our endpoints here from A to B. Let's say that's A and this is B here. We know that as we go from A to B, that radius, or the radii of each circle varies according to what? Which one? F of x, right, yeah, the height from the function to the axis, top minus bottom, f of x minus 0 is the radius. So that's really 2 pi times f of x. Okay. And then so notice all of those circles are sort of extended out, like these circles up here with the cylinder were extended in the direction h high. Well, this circle, this is equivalent to the height, but it's not quite the height because it's not a linear dimension. But can we measure that distance from there to there? Yeah, we just did that. It's the length of the arc, right? So it's 2 pi r times L, which is the arc length, which is defined as 1 plus f prime squared. So there's our 2 pi r times a length. Circumference times the length gives us an area. So that's what we're looking at there, is the surface area formula. Once we sum all of those up, we put an infinite amount of those in there. And that's what we have. We have our integral formula for the surface area. But that's I think, another way to think about it. And so when we look at that formula, that's again the derivation from your textbook. But when we look at the surface area formula, I mean, yeah, it looks a little bit difficult to manage, but at least we know where all of those components are coming from, okay? So, you know, that's like the circumference or the length of each circle. Here's, again, the arc length, this piece right here. And then the dx is just the really tiny thicknesses of our circle. So the way these happen to play out in 6.6 is that a slight modification when we add 1 here. So when we add 1 inside to f prime squared, we want to add 1. And I think at least initially this makes it a lot easier to compute all of this stuff. Add 1 in the form don't know, let's call it g. Let's call it g of x over g of x. Because we'll end up adding 1 to f prime squared, and so that'll involve some function of x. So when we do that, again, nothing exotic here as far as what we have to integrate because we're limited. But when we do that, typically what happens is that this f of x on the outside will cancel with our denominator here, and then you end up again with a nice square root and something that's a little bit easier to compute. Okay. Let's also specify. So f is a non-negative function, continuous first derivative from a to b, and we're finding the surface area generated when the graph of f on AB is revolved about the x-axis. So the surface area with respect to is found with respect to the variable of or the axis of rotation. So I know when we had like shell and washer method, you had to be careful of which variable you integrated with respect to. Surface area is just straightforward. If you revolve it around the y-axis, you integrate with respect to y. Let me see how many examples we have here. Okay. So we'll start with this, a simpler one, kind of see how this works out, and then give you an opportunity to attempt the next question. All right. It's kind of the same procedure. We've got the root of 1 plus f prime squared. Let's just go through that procedure like we did in the last section when we found arc length. So just getting this ready to take the derivative. We'll express it as a power. So what's y prime?
Two-thirds 4x plus 6 to the 3/2.
That's antiderivative, where you add 1.
Oh, we're doing it.
Yeah.
So, 2 over that to the negative 1/2?
2 over this to the negative 1/2?
Or 2 over that to the 1?
Yeah. So power comes out, multiplies the inner function to the subtract 1, or 1 less power. Don't forget the chain rule here, times the derivative of the inside function is 4. So then we combine the 4 and the half, so we have 2 times 4x plus 6 to the negative 1/2, or 2 over 4x plus 6 to the positive 1/2 or the square root of that, however you like. Many ways to represent that, I guess. Okay, so there's y prime. We need to square y prime next. So we square y prime, we end up with 4 over 4x plus 6. And then we have to add 1. But here we're going to add 1 in the form of 4x plus 6 over 4x plus 6, just so we can combine everything. So we have 4 plus 4x plus 6, we have 4x plus 10 on top, over 4x plus 6. Questions on what we've done? So there's just a slight modification. And we see why when we put all of this into the surface area formula. So the surface area is 2 pi times the radius, which is given by f of x, times the arc length. So that's times the square root of what we just have, 4x plus 10 over 4x plus 6 dx. And it said the interval is 0 to 5, so those are our bounds from 0 to 5. Yeah.
Wouldn't the bottom be 8x plus 12?
What bottom? Oh, no. Because when you add fractions, you just add across the top and you keep
Oh,
the
yeah.
bottom. All right, so see, we added 4x plus 6 over 4x plus 6 as 1, so we can get this thing to be just something over 4x plus 6. And so now when we multiply this by f of x, see this root out here and the root below just cancel out. So this is really square root of 4x plus 10 over the square root of 4x plus 6. So this 4x plus 6 cancels with this. Or sorry, the roots do. So we're just left with 2 pi times the integral from 0 to 5. The square root of 4x plus 10. So that's a much easier thing to work with. Questions on that? Easy enough? Maybe. Okay. So we get here, not an exact answer, but, well, I guess our exact answer, pi over 3 times 30 root 30 minus 10 root 10. Which is about 138.957, whatever they are, square units. So this is an integral where we would have u substitution involved. And so forth. When we're doing the u sub, so these original boundaries 0 and 5 are for x. So once we get our u substitution, our x equals to 0 goes in our u substitution. So if we're keeping everything in terms of u, the lower limit is when x is 0, which gives us a u value of 10. And an upper limit, x equals 5, gives us a u value of 30. So those values on u would be from, 10 to 30. Or if you just, some people convert back to 0 and 5 once they resubstitute, which is fine too. Okay. So not a whole lot of modification from what we've done in 6.5, but a huge difference in what we're actually describing. So, no one has any questions on this? Then the next question is kind of similar, but number 14 is a little more involved. I want you to try that either together or on your own.
Oh, this is always square root. But in the last one. Square root, square Take 5 grand. And those two cancel.
Yeah, I was like this way wrong. So it's like the or now these two things. And there was one out that just I was breaking up
Yeah. I was looking at it. I was like,
Oh, he's 21 as well. 15.
Yeah, that's what I'm doing.
Wait a minute.
Oh, ours?
I'm already there.
Yeah. I'll wait for that. So. Okay, okay.
So I think the one half.
Okay, so it's just regular, basically, just the function minus the zero.
Derivative.
Oh, this is regular.
Derivative then the sine minus
Right, yeah. Well, yeah, so it'd be like x added minus the x-axis, which is 0, so it would just be that. Okay,
Oh, yeah.
You get
Just fun. This guy. That's just went wrong, so.
So it probably works
Yeah, I might
out.
actually like Oh, you're right. So, okay, these are my questions. So, like, you just cut this on top of the bottom by 4. And then still one price. It's just because then you're not able to, because the reason I'm doing that is to get rid of this denominator.
the thing we just had on page. Wait, it's one less than. No,
Do you think you can afford it? Wait,
I already got it.
wait, but the 4 would just be there by itself, like, right? I think I'm stupid because I'm pretty sure the 4 just chills, right?
You won't fix the 4. I'll take the 4.
Right, so that's like, kind of canceled out. And that's
Does that still have So like, don't you go and see your
Yeah, no, yeah.
because like, that's like the whole point of it. You have the one.
Square root 24.
Yeah.
Oh,
Yeah.
I got
So
you.
you're right. Just make the fit on it. You're right.
So it's 2 pi
Through the square root of 1.
The reason you have to,
Later.
you have to change that.
Change. So it's just that.
So like, this one.
Why is there a 3 next to
Let's go with glasses. For which one? The 565? 665.
Oh, okay. Well, I guess I should.
That's the only one I haven't done.
But it works, hopefully, yeah.
Except like this way.
That alone. There's no way you could remember that. Multiplying this and you're looking at the. And sometimes you're like, like telling you.
I can't even tell.
It's only the math lab.
Yeah, yes. Well, it's actually just
Yeah, no, you said this whole thing should be behind the roof, so.
Like, so you're adding one, it needs to be a common
This.
denominator. Like there needs to be a common denominator.
I know we have two things.
Can I just see what you're
Oh, yeah, so I can see it.
actually, that's how it works.
Given ours,
Because it's supposed to be functional.
well,
Okay, so
Yeah, they usually multiply that.
Oh, I actually.
okay.
Oh, I see what that is. Oh, okay, did you take the derivative?
there it is.
Right, so like this, when you take the integral and add it,
Oh, you're set, yeah.
so it'd just be.
First physics test is like
Step.
It's the cross terms. So you take this physics.
Yeah.
This one.
That was part of just
Right, this is the whole classic movie.
I don't know. I just got 25.
And it's about like, I have like 4 pages.
Just two times.
Wait, so where do you put it? Let's do this.
I saw the birth. Did you apply
I
it?
get there on like 1s to. I've done like, yeah, I've done already like.
And then the bottom square?
Yeah. Just doing it. So, it's true to all our things like that.
So, that's 2x squared. That's gonna be 5
You haven't applied yet?
that should be
Where are you
20.
my associates? My associates.
Right there. And then that'll be plus 4x squared.
There you go.
I think it's in terms of
But like I have about 4 credits. I have this as a one. Well, the end of the semester.
Okay.
As soon as I can write this, as soon as I can write this thing. I'm like, let me ask.
Yeah, and I hit there.
Whatever I got.
That's exactly what
Yeah.
I didn't bother doing it.
I saw that too. I did initially predict square like 2.
Yeah, that does make sense.
Yeah, like 2 people. Like 2 when I squared
Yeah,
it.
to know what type of process.
It's just true or false.
Some of those aren't there.
Those ones also do.
Yeah.
Who am I to say what's true, you know? My favorite is the one that you're really at and there's something like zero.
Wait. There's almost always like 1 or 2 zeros right now.
And I was like, why do you give me no points? Like, even like I'm good for the question, right? No points. I was like,
Oh, yeah, that's fine.
I was solved.
So it'd be 5 or 2 eggs.
He always finds me.
What were the 2? Yeah, they just stare. So I would like, if you'd always stare at them, so I never got to like looks. He was like, I know he was like borderline.
Cody's at -1/2 on that. On the white prime squared. Should be -1/2.
I was like,
Where? Here?
Power? Yeah.
Oh, we squared it though.
good laugh.
So we multiplied that power by 2, which gives us -1. Yeah, we just squared each factor.
Wait, what's the Where I'm going wrong. Oh, so it's 5.
Yeah, I was like,
Oh, wait.
I
I haven't taken it. What is
Mine should be.
So I realize some of your algebra might be different, and depending on how you combine stuff. But the main thing is that we all end up integrating the same thing, and that's what we'll use as a check, because everybody prefers to write things a little bit differently. I will tell you, however, the denominator, the 4 times 5x minus x squared, personally wouldn't multiply any of that stuff out, because we got to remember all of this stuff goes into a radical. All of that stuff is going into this radical here, but then we have to multiply by the original function. And since the original function already contains the 5x minus x squared, I'm just going to leave the denominator as is, just so I can see that that will easily cancel out. So you gotta kind of think ahead a little bit as far as what else you have to do. There's a tendency just to get bogged down in all of this stuff and just kind of know, like, when do I stop doing stuff, right? Or when is it simplified enough? And really that's a question that you have to determine depending on what problem you're working on. There really is no like hard and fast answer for that. So 1 plus f prime squared gives us what, 25 over 4 times 5x minus x squared. So that's all we've computed there. That was all of that effort. Yeah, that's just all that effort to compute just that. And then we're ready to insert into the surface area the original function times our 1 plus f prime squared and then our bounds were from 1 to 4 and we have our 2 pi times our function times our arc length. So again, your expression might look a little different depending on how you chose to expand or not expand stuff. But we have this root canceling with this root. So all we have is 2 pi times the integral from 1 to 4. And we left over here is square root of 25 over 4. So all of that stuff, f of x times the arc length, simplifies to 5/2. Which is good because that's super easy to integrate. Even the more simple function that we had in the first example was a little bit more involved as far as like the integrand, what we had to integrate. So, okay, are there any questions on what we've done, or steps? Again, if you're pulling this as a constant out, and integrating with respect to x, but remember it's a 1 here. There's 1 dx. We're just going to add, think about that as 1x to the 0. Just a power rule. So 15 pi. Everybody cool with that?
So all the steps are the same essentially from 6.5.
Right, yeah.
Except for the putting the 1 in different terms.
Yeah,
I got you.
right, yep. And the addition of multiplying that f of x in addition to, yep. Sure. Tell me when. There.
I can't remember. It's just
The book has got
like
I'm like, give me an example where it shows me, give me a step so I can figure it out myself. You know, on my We're also gonna slide.
Every girl applying for
No. I need to get. I don't know. I really do try to get. I was gonna You want, I want you to go, like, I'll show you.
even if you have this like,
It starts here.
I can see it. It's like a tongue trick question.
Okay, just won't say a whole lot about this example, but it does ask you to find the approximate volume of paint. So just be mindful here. You now have to find the surface area, and then multiply by the thickness. So there's your thickness there. And they try to be tricky because they give you 1.5 millimeter layer of paint, but then they say assume X and Y are measured in meters. So you want to keep your units consistent. So we have the meters here converted into, or millimeters rather, converted into meters there. So really the bulk of this problem is to find the surface area of that, because the solid, I guess, that's generated by revolution, we're going to then put a 1.5 millimeter layer of paint on that, and then they want to know what that volume is. So that's just kind of spelled out here, and I'll mention or tell you that the surface area is 320 pi. So this, again, we see another function that involves a radical. It's very similar to the first two examples and how it all kind of works out. So once we talk about something in Chapter 8, there's some of these surfaces of revolution that we can revisit. One of them is called Gabriel's horn or Gabriel's trumpet, I think. I forget, Gabriel's horn. But it's a surface of revolution where you can actually compute the volume. So it has a finite volume, but it has a infinite surface area. So like you could fill the object, but you could never paint it. We do run into some pretty neat paradoxes, but once we talk about integration techniques, then it really opens the door to like what other kinds of things we can look at. Anyways, if you have any issues with that problem, feel free to ask. Similar example too. This one says find the area of the surface generated when the curve is revolved about the y-axis. So with surface area, the axis of revolution and the variable of integration is the same. So we're revolving this around the y-axis. We want to integrate with respect to y. So before we go on finding the derivative and squaring that, we need to make sure that our function is in terms of y, not x. So in preparation for that integration with respect to y, we solve our given equation, x squared over 4 for x. And put the bounds in terms of y. Because our bounds are also given to us in terms of x. So integrating with respect to y. Multiply by 4, take the positive square root because it's in between 2 and 4. So don't worry about the negative square root. So what we have is x is equal to the square root of 4y, which is 2 root y. And our bounds are just given to us by that equation. So if y is x squared over 4, first bound when x is 2, and when the second when x is 4, we can get those in terms of y. So if x is 2, 2 squared over 4 is 1. And x is 4, we have 16 over 4, which is 4. So those are the bounds we want to use in terms of y. So just sort of have to rearrange what they gave us originally. Now we can say find the surface area of this function, x equals 2 root y, when it's revolved around the y-axis from 1 to 4. So that's what we're working with. Does that make sense? Does anyone have any issues with that? Questions? Comments? All right. So that's our new problem that we need to work with. Same procedure, we're going to find the derivative. So what's the derivative of x with respect to y? I'll just leave this here. Yep. So you have 1/2 times 2, y to the negative 1/2. Or 1 over square root of y. Okay, so that's x prime. Take x prime squared. That's 1 over y. Add 1. That's y over y. Okay, so after we add 1, we have 1 plus y divided by y. And that's the thing we're putting into our square root, 1 plus x prime squared. Bounds were 1 to 4 in terms of y. Our original function was 2 times the square root of y, and then we have to multiply by that by the square root of 1 plus y over y dy. we have cancellation here. Constant is 4 pi from 1 to 4. And then we're left with the square root of 1 plus y dy. All right. Again, same idea. Just be mindful of the variable you have to integrate with respect to. I guess, do you want to work this out or just try that later?
Or now?
Yeah. So how do we integrate that? Yeah, use substitution. If you don't need a use substitution here because it's a linear argument, that's fine. You can just go straight into the antiderivative. So use 1 plus y, which means du is dy, which means that the integral turns into 2 pi times the integral of the square root of u, so that's going to be u to the 1/2 du. If y, the bounds are on y, we're 1 to 4. When y is 1, u is 2, because it's just plus 1. So we go from...
Shouldn't it be 4 pi? Shouldn't it be 4 pi?
Oh yeah, it's 4 pi. I don't know why this 2 is here. Yeah, thank you. U is 2 when y is 1, and u is 5 when y is 4. So we've got 4 pi. Antiderivative of u to the 1/2 is u to the 3/2 times 2/3 from 2 to 5. So I would compute it as that's 8 pi over 3 and u to the 3/2 from 2 to 5. And I think we've seen this 3/2 scenario. If you needed an exact answer, remember some number to the 3/2 is just that number times the square root of that number, right? So any number to the 3/2 is really just the square root of that number cubed, which is really just the square root of that number squared times itself. The square root of the number squared is just the number. So that's the number times the square root of itself to the 3 when we're doing the 3/2. So you got 8 pi over 3, 5, so it's 5 root 5 to the 3/2 minus 2 to the 3/2. So there's our exact answer, and just be careful of how it wants you to express your answers. Or if it says round, then of course we could approximate. You should just be able to get the exact answer though. I wouldn't depend on my calculator to get it for me. 69.968. Okay, we're talking about a surface area, so we're talking about square units, whatever they are. Okay, sorry that we went a little bit over the hour mark. Do y'all have any questions on what we've done? The mechanics are tedious and cumbersome, right? But, you know, again, taking away from the big picture, we see another application of integration. I mean, hopefully you find some of this stuff cool outside of the mechanics of computation. That's not that cool, I don't think, but, so it is. So at 6-7, we look at physical applications, and I mean, although there are some exercises in the textbook that kind of come back to these, primarily this is our only section where we do look at physical applications. There's so many of them, and what I always tell people is that if some of this math that we do, it's just math, right? It's like, hey, here's the foundation on how to do this stuff, and then sort of the context gets lost in where this could actually be applicable. And so if you're ever curious, I would just recommend going to the textbook and looking at the exercises, because there's a lot of applications in some sections where you could actually just, read them. You don't have to work them. If you want, you can, but you can just read through them and see, okay, well, hey, I can use whatever integration by parts applied to this particular physics problem or whatever it is. So if that's ever a thing for you, I highly recommend doing that. But and again, we're limited in the scope of what we can actually look at due to the fact that we're limited in our integration techniques. So we're going to look at mass and density, force and work, and force and pressure. So the work and the force we'll look at in the context of springs and Hooke's law and lifting problems. Like how much work is required to lift this water out of this, trapezoidal trough or something like that. Force and pressure, we look at basically one application. It's just the force on, I don't know, typically they're dams. And if I can remember or actually locate, I had a couple of videos that sort of explain that hydrostatic pressure. Because the dam is like a three-dimensional object, and there's all this water behind it. But really, what's contributing to the force on the face is just the surface area of the dam itself. It doesn't really matter how much water is behind it, which is kind of counterintuitive. But in one of the videos, they made an analogy of, would you rather have an elephant step on your foot, or I don't know, Shaquille O'Neal in high heels step on your foot? I don't think they use Shaquille O'Neal, but... And then they say you'd want an elephant to step on your foot because the surface area of its foot is wider, right? If Shaquille O'Neal's stepping on your foot with a high heel on, all of that pressure is just concentrated right there. So it has to do with surface area. I'm assuming everybody knows who Shaquille O'Neal is. I don't follow sports, but sorry for the sports analogy.
What about an elephant wearing a high heel?
What about what?
An elephant wearing a high heel.
Yeah, you probably don't want to do that. All right. And so our mass and density is the first thing we look at. And it's really, these applications are pretty straightforward. There's not a lot we can do. So mass is just density times volume. Density, whatever, measured grams per cubic meter. And then, of course, a volume would be measured in cubic meters. And then that would give us just grams. Sometimes, however, though, depending on the context, density could be in a slightly different context, not in terms of volume, but it could be presented in terms of area or a linear measurement. So I guess another way to think about that is, well, let's say here that also we're going to call our density function is, the Greek letter rho, which looks like a fancy P. something like that. So we'll just say mass is density times volume in a certain context, or we could say mass is density times area, or mass is density times length. So in that sense, density would be grams per meter squared times an area, meter squared, so forth. We'll see an example where we are given a linear, for that linear case, where density is measured, what is it, whatever, grams per meter or something like that. Okay, but that's for uniform density. So what if the density varies? Like, just imagine we had this steel bar that wasn't made uniformly, and the density varies from A to B. The idea is similar to the ideas that we've looked at so far, where we say, well, we'll just cut that up into a bunch of really small pieces, and then we'll sum all of that stuff up. Okay, so here's some certain cross section that's super small. Here's a super tiny measurement dx, and then we just sum all of that up. So we would say mass is the sum from k equals 1 to n of our density function. They're using x bar, so we'll use density, because density is varying, so we have a function that describes how it varies, times.
Ladies and gentlemen, the library is now closed. Please get your belongings and proceed to an exit.
Yeah. Thanks, dude. Okay, and then we let n go to infinity, the number of cross sections, or little rectangles, if you will. And I don't have the formula. So, okay, then that turns into our definite integral from A to B, density times length, or density times area, or density times volume. So that's our mass calculation. And really we just get one type of problem from this. So for example, the mass of a thin bar with density f of x being x cubed from 0 to 2 and x plus 6 from 2 to 5. I mean, even that's a pretty simplistic case. So there, our function is x cubed from 0 to 2, and then x plus 6 from 2 to 5. So the mass is the density times the lengths. We sum all of those up. So we actually have to break this up because we have two separate functions. We'll compute the mass as the integral from 0 to 2 for the density function x cubed dx. And then we'll add to that the mass for the other portion of the bar. So from 2 to 5, integral from 2 to 5 of x plus 6 dx. That's about as complicated as those things get. That's 65 halves. We weren't given any units, so whatever the mass is, grams, kilograms, etc. Okay. So are there any questions on that? Very limited. Okay, work and force. We'll first look at the work for springs that involve Hooke's law, and then we'll look at pumping water out of a trough. So our units here for work are measured in joules. And joules are kilograms meters squared. Meters cubed per second squared. No, it's meters squared per second squared. Sorry. Thinking of something else. Meters squared per second squared. Force is measured in newtons, capital N, kilograms, meters per second squared. And then distance is measured in meters. So joules and newtons, I'm assuming y'all are all familiar with that. Those are the units we stick with because, as you know, dealing with units is sort of another problem in and of itself. So that'll be pretty consistent. Okay. Yeah, that's a constant force. So we want to assume that now what happens if we vary that force? So if we vary the force on this block from A to B, we're still doing the same thing, and we're just slicing that up into these rectangles. And we're saying, okay, well, what's the force? The force is determined by this function, capital F of x. The distance that each one of these cross sections move is just some distance in the x direction, and so we just sum all of that stuff up. So work is simply the integral from A to B on the force function across a small distance. So there's your force times distance, and then we're summing all of that up. Of course, depending on the problem, the force function might be something you have to find. Sometimes it's given. It just really depends on the problem. Okay. In the sense of our spring problems, the force function follows Hooke's law, which we'll look at in a second. But the way these spring problems are set up is that there's an equilibrium where the spring is in its natural position. We call that equilibrium. When we compress the spring, push it behind the equilibrium, we're going to consider that distance x, or that displacement, is negative, and stretch it beyond the equilibrium, that displacement is positive. So that's the convention and how it's set up. Okay. So here's Hooke's law. It just says that the force is k, which is the constant of the spring, times x, which is the distance. So if we're dealing with springs and shock absorbers and that kind of thing, then we need to remember that default work is the integral of force times dx, that force function automatically turns into kx. Okay. So for example, we're given a spring constant of 400 kilograms per second squared. Find the work in joules required to stretch the spring 10 centimeters beyond the equilibrium, and compress the spring 2 additional centimeters when it's already compressed 3 centimeters. So you got to pay attention to the units is the thing with physical applications. So they say find the work in joules, which is kilograms meters squared per second squared. That's too late. Okay. So that's what we need to work with, those units, and be mindful that they've given the stretching and compressing in terms of centimeters. So we need to convert those things into meters, right? Okay. So there's work equals force times a distance. Our force is again K times X. That is, our work is found by integrating 400x dx. We're given that K. Now, remember the X is negative for compression, X is positive for stretching beyond equilibrium. So when we look at A and B, the only thing that's going to change here in this setup is the bounds. The spring constant, the force is still, the force function rather is still the same. Here's part A. So the work required to stretch the spring 10 centimeters beyond equilibrium, what would our bounds look like there? 0 to 10? Yeah, remember those are in centimeters. We want things in meters. So beyond equilibrium, it starts at equilibrium, we're stretching it so that's positive 0 to 0.1 meters. So that's our setup for that one. Does that make sense? Hopefully it's pretty straightforward. Okay. So the answer is 2, but it's joules. There's our work in joules. Okay. Let's just kind of reconcile our units because all we're doing is multiplying this stuff and the integral just means that we're adding. So the 400 had units of kilograms per second squared. That's kilograms per second squared. X is measured, even though they gave it to us in centimeters, we're going to convert it to meters. So X is meters. And dx, again, is just some small distance in the X direction. That's another meter. So we have kilograms meters squared per second squared. Any questions? Okay, so what will part B look like then? What are our bounds? Okay, negative 0.3 to negative 0.5. What do y'all think?
Should be 0.05.
0.03? Yeah.
0.5 to 0.3.
Yeah, because we're looking at 2 additional centimeters and 3 centimeters. Okay, so if we make that change, does that sit well with you?
Wouldn't it be? Yeah, when the negative 0.05 get involved, because that's the bar.
Yeah, so we're compressing it 2 additional centimeters when it's already compressed. So it's compressed here. Let's look at it this way. Here's equilibrium. And we want to compress it. It's already compressed back here. So we want to compress that 2 additional centimeters. Right? So we're going in the negative direction. So I think we can all agree that these are the correct bounds. But how the order is now in question. So would it be from negative .03 to negative .05? Or would it be the other way around?
Well, we would expect our units to be positive in our answers, so we definitely need to flip it.
Okay. So we need to flip it? Y'all agree with that? Disagree? Don't know.
It's that they're right. Because, in this case, the .05 is going to be the greater force, so then you're going to subtract out the lesser force. You should have a positive answer.
Right. So I mean, if you're unsure, then you just, like, I guess you could work through this and see, does the work come out to be negative? And should it be negative? Or does the work come out to be positive and should it be positive? So does it make sense to say negative work? I mean, I guess in some senses it does, right?
When it comes to like directions,
Right. So when it says like the work, maybe we say we would have to quantify that, the work done against gravity. We could say that that's
or against the spring.
or against the spring, or yeah, whatever we're working against. We'd have to quantify that. So I'll tell you, typically here for us, the work is positive because we're already assuming that it's the work against gravity, not with gravity, right? Okay. So I don't know if we reached a consensus or not, but some people said we should flip the bounds. Some people weren't sure. So, I mean, just think about it for a moment. Maybe write it down. I don't have any figures or anything to show for this, so I'm just gonna think about it. You can compute it if you want. It should be positive work. And think about the starting point and the ending point.
They should always work. Even
If it's already compressed 0.3 or 3 centimeters, isn't it technically right there? So we're starting right there, and then when we compress it back this way, so we're moving from 3 centimeters to 5 centimeters in terms of compression. But it's backwards of how we normally think about, like find the area from -5 to -3. You would say, well, it's the integral from -5 to -3, right? Because we're going this way. We're going from here to here. This time we're acting this way, though. We're starting at 3 centimeters. So we're starting here with our lower limit. We're compressing it another 2 centimeters, and we're ending there. I mean, maybe that's a better way to think about it. I don't know. So the fact of the matter is that the bounds are fine as they are. Start, end.
You said that when you're compressing stream, the work is negative?
No.
No. What were you saying? You said when it's stretched out, it's positive. You were just talking about the direction.
Just the direction of movement. So to the left of equilibrium, negative to the right. So I said, we just kind of asked the overarching question, does it make sense for work to be negative? And most of the time it doesn't. I mean, there are some instances where maybe it would, but generally work is positive. So this is fine, as is. Start, end. 0.32 joules. All right. Anybody have any questions about that? Yeah.
In this case, aren't the bounds showing us whether we're compressing or stretching?
Yeah.
Like if it was stretching, it would go from 0.5 to 0.3, assuming that equilibrium is at 0.10 or something.
Okay. Yeah, you can think of it that way. And then in this case, since it's going from this negative value to something to the left of that, if you will, then that's just showing the compression. But you're right. If this were a stretch, then it would go from we would stretch it from 0 to 5 or from 5 to 10, right? If it's already stretched 5 centimeters and we want to stretch it additional 10 centimeters, then our bounds would go from 5 or 0.05 to 0.1. Okay. A similar problem with, this time though we're dealing with pounds and inches. So in the last problem we were actually given the spring constant. What is pounds though? What is weight? Yeah, the weight is already a force. So the scale is, I guess it doesn't say assume Hooke's law applies, but okay, it does. All right, good. So the idea is that now we're measuring weight, which is already a force in and of itself. So it says a 270-pound person, this is force, compresses the bathroom scale 0.09 inches. And so that's our X. So how much work is done compressing the scale if a 330-pound person stands on it? So what do we need to do here? Find the spring constant, right? Because we're still talking about work, obeying Hooke's law. I mean, we can figure out these bounds later, but that's what we're dealing with. We have to have a function to integrate first. So with this first bit of information, we have F and we have X, and we'll use that to find the constant, the spring constant. And, you know, just be consistent with your units. I would say that since it's a force down, that we should say that's negative 270 equals to K times compressed negative 0.09. And then we can find K to put that into our work, or our force function rather. So that you should get that to be 3,000. K is 3,000. Pounds per inch, yeah, because we're dividing pounds by inches.
So why was K pounds per second square in the last example?
Because the spring constant was given to us in kilograms per whatever it was, second squared.
So the units don't have to have a denominator squared necessarily for K?
Not necessarily, yeah. Yeah, it's just like, particularly with these units, if we want to measure that in joules, then yeah, you have to have that. Because the seconds don't come anywhere else, from anywhere else. All right, so now we have our work is the integral 3,000 times x dx. And so how much work is done when compressing the scale when a 330-pound person stands on it? Well, really all we have to do now is find the bounds. So how do we find the bounds?
270-pound person, 0.090 to 330 over X or something like that.
330 over X?
So you got like 270 over 0.09.
Yeah, okay. Yeah, I see what you're
You
saying.
just take a ratio.
Yeah, you could relate that back to X. So say that again, you would have what? You would have 3,000.
270 over 0.09 equals 330 over X, and then you just cross multiply and divide.
Yeah, that should work. So again, we're talking about this 330-pound person on the scale with our spring constant, and we want to figure out what this X is, right? Because if no one's standing on it, it's at equilibrium, it's at 0, and when we compress it, that's what we're going to find here. That negative 0.11, yeah. So that's how much the scale is, displaced as that person, the 330-pound person, stands on that. So from equilibrium to, and it's compressed that much. That's it. So with the spring problems, shock absorbers, scales, that kind of stuff, Hooke's law problems, I should say, the bounds indicate the amount of compression or stretching. The spring constant, the force function, however you look at that, is always the same, as long as you're dealing with the same scale, spring, shock absorber, etc. So this is 18.15. $18.5?
No, that's right. But like, what are the units?
So what are the units? So pounds per inch squared. The units for the spring were pounds per inch. The units of X are what? Inches. The units for dx? Inches. Yeah, remember dx is just some measurement, a tiny, tiny measurement in the X direction. So we just have inch pounds. Or pound, whatever. I don't know what they call that. That's why I didn't study physics, because I hated units. Like, I don't care. What's the number?
Generally in
Like
physics-
inch pounds. I don't know. What does that mean?
Generally in physics, you don't use inches or pounds.
Yeah, you use SI
Kilograms.
stuff. Yeah. And we're not on, we have our own system of measurement while the rest of the world has their system of measurement. I don't know. It's stupid. All right, so there we are. Okay. Questions on this? All right. So then we'll move on to the lifting problems, and they're a little bit more involved. So the lifting and the pressure on a face of something, those are more involved because it involves us looking at these sort of cross-sectional area type things. So this is our, let's just use this as our tank, and here's this outflow pipe here. So there's where the water comes out. And we want to know how much work is required to lift, let's just say all of it. How much work is required to lift all of this water out to the outflow of that pipe? So the way we tackle that is we just kind of, like we've tackled everything, we look at this little cross section here, and then we just figure out how much work does it take to get this cross section out, and then we can sum all of that stuff up. All right, so let's start with, I'll come back to this figure in reference, but let's start with the fact that work, just start out simply here, is force times distance And here I'll be a little more specific. Distance, force times distance of lift. So we'll just say that for now. Force is mass times gravity. Distance of lift, let's go ahead and see if we can address what distance of lift is in terms of this right here. So remember, if my cross section is running this way, it has some thickness dy. So we just want to think about that cross section because in fact we're doing it to every cross section. So what height do we have for this particular cross section? Maybe think about when we were looking at the shell method, how we actually measured the radius. So what's the height of that particular cross section? It's just some measurement y, right? If I told you that's a y value of 3, you know exactly where that cross section's at. Remember, we wouldn't say x because we want to integrate with respect to y. So that's from this to this, that's just some distance y, but we're pumping that out to the top of this line that we're calling y equals to h. So really what we want to measure is not this distance, we know that's some unit y, but what is this distance? Yeah, so we see that, somewhere they have that, but there's h minus y. That's the distance of lift for each cross section. Is everyone cool with that? Does that make sense? Are there any questions? So we had force times distance of lift. Force is mass times gravity. We're going to break down mass a little more. So mass, we're going to break down as density because we have to consider the density of the liquid that we're pumping out times volume. Times h minus y. Again, similar to when we were finding volume in chapter 6. Or, do what? Oh, yeah. Thanks. We keep gravity out here with our constant. we instead of thinking about the volume of the entire thing that we're dealing with, we're slicing into that. So we really only need to think about the surface area of the cross sections to give us a picture of the volume. So we're going to break volume down. We have our gravity times our density. We're going to break volume down into area of the cross section. And thickness. So if we multiply an area by a thickness, we'll get volume. Times the distance of lift. So hopefully that makes sense why we broke it down that way. Again, just think about the volumes we looked at in 6.3 and 6.4. We thought of the general slicing method where we summed up the areas times the thickness. Okay. So what else? Would the thickness of our cross sections vary here as we cut through that particular object? Would those thicknesses vary? No. Would the area of the cross sections vary? Yeah, because the area of this circle at the very bottom is quite a different area than the area from the circle at the very top, right? So this, these circles are described by the area function, but it varies, so it's an area function in terms of y. So that's a of y, and our thickness we'll just call dy. So then putting this together, we have the work, and we'll just say it's the integral from a to b. We'll talk about that in a minute. Density times gravity times your area function times h minus y, distance of lift, times the thickness. And personally, I would put I always put the constants out front, so we have density gravity out here. Density times gravity here. So we just need to find the area function, the area of the cross sections, and the height. So that's the formula that we're going to work with for these problems. So this, our row density is the density of whatever this is. Density of liquid. Typically it's water, and they'll give you that in the problem, but it's, what I think it's 1,000 kilograms per meter cubed. That's how the density of water is measured.
Squared or cubed?
It's cubed. If it's some other kind of thing, then they'll also state that, but typically it's water. So we've got density gravity, of course. We're going to leave gravity as positive because our work's going to come out as positive. If gravity were negative, then the work would come out to be negative. So when we see this work with a positive gravity and this work comes out to be positive, then we just assume that that's the work done against gravity. Okay, so mass density, A of y, as we said, A of y is the area of the cross sections. And A of y, of course, depends on the tank or the vessel that's containing the liquid. H minus y is the distance to the outflow. And usually it's the top of the tank. But not always. Yeah. A is the bottom of the tank. And B is the top of the outflow. I might as well specify here too, dy is the thickness. Of each cross section. Of course, that's in the sense of it there being infinitely many of them.
Wouldn't B just be the water line?
Well, if you have to pump it out, like this depends. If like the top of the tank is the top of the tank, then yeah. But if it has to,
like in the picture, the water came up so high. And
let's think about that. Since we are using this picture here.
So there's a gap there.
Yeah.
Right. So B would be the top of the water, right?
Yeah, here. Right. Yeah. So in terms of Y, A, and B. Yeah. So what do we have? Oh, okay, yeah, I'm sorry about that, yeah. So B is to the top of the tank, not the outflow, sorry about that. Thanks. Yeah.
So we're integrating from A to B, which means we're like starting with the water on the bottom. I thought that we would start with the water up here because that's what's being drained out.
Well, it's kind of it's getting pumped out, right? So just think about this little cross section here, and we're pushing it out this way.
All right.
So yeah, all of these Y values range from A to B. Here. All right. So the when we look at the force function, or the force integral rather, you'll notice that it's very, very similar to this. The only thing we have to modify with force, like we said, we're talking about the force on the face of something. So like we're measuring the area, and so we just break down area into a length times a thickness. So really the only difference with the force versus the work, because the work is a volume that we're pumping out, is this function right here. The A of Y function, when we look at the force problems, will just be a width function instead of an area function. It's the only difference between those formulas. Of course, maybe from your physics class, you know of other ways to compute work and force. Again, this is limited for us, so that's how we're going to look at it. We got 5 minutes. We can probably start this, perhaps finish this one. And then our next example is similar with something that's a little bit more, I guess, a little bit more involved as far as the container. So the water is at a height 8, radius 2 meters for the tank. The tank is full of water. How much work is required to pump the water to the top of the tank? And we'll answer that question. And then will it take more or less or the same work to pump out the water if the tank is only half full? So this is our, we'll just call this part A. And so we'll remind ourselves, work is the density times gravity integral from A to B. Area function times h minus y dy. All right, so area function is the area of the cross sections. Well, all of our cross sections, if we cut through here, would actually just generate a circle. So the area function, or sorry, the area of the cross section rather, is pi r squared. Fortunately for us, though, this doesn't vary. All cross sections have a radius of 2. Okay, so the area function is constant at 4 pi. What would h minus y be? Is what? Sorry, I didn't. 8 minus y. What do y'all think? 8 minus y for the distance of lift. So if this is our cross section has some height y, and this is a height of 8, then the distance of lift for that cross section is just top minus bottom. 8 minus y. So area function, got that, h minus y, we got that. Everything else we have too. That's it. So then work is, we have density, which is the density of water, times gravity, times the integral from where to where? 0 to 8, yeah, might as well keep it simple. Set that thing on the x and y axis, right? I mean, you could say it's the integral from 8 to 16 if you want. Area function, distance, dy. Everybody all right with this setup? So compute that rather large number. 3940 813.825. What would our units be? Somebody's getting out of class a minute early. What would our units be? Kilograms per meter something, yep. The density, we had kilograms per meters cubed. Gravity, meters per second squared. What are the units associated with 4 pi? Which one?
Radians.
Not radians. Radians don't actually have units. 4 pi was our area, right? It's meters squared. 4 pi was our area function, meters squared. What units are 8 minus y? Meters, that's the distance of lift. And the units for dy, also very tiny meters. So we have our meters, excuse me, meters cubed. Crossing with that meters cubed, we have kilogram, meter squared per second squared. All right. We'll talk about the rest at some other time. Sorry, I owe you a minute. Let you have a minute early one day. All right, have a good weekend.